So this week we're looking at the synthesis of an imine complex and a change in its physical properties, namely a change in the color of the compound. But I wanted to start by talking a little bit about the importance of chemical synthesis first. And my favorite example for this is always to go back to this molecule Taxol as drawn on the slide. Now, Taxol is a natural product that's isolated from the Taxus brevifolia, which is also known as the Pacific yew tree. And what makes Taxol so interesting is that it's an incredibly potent treatment for ovarian cancer, and it's also been used for breast cancer, and it's been approved by the FDA since 1992. Now, what does this have to do with chemical synthesis? Well, as it turns out, this is a great treatment for treating cancer, and yet the Pacific yew tree itself, if we were going to harvest a 100-year-old Pacific yew tree, we would get about 300 milligrams of Taxol. And that's about enough for a single treatment. So this really, in my mind, highlights why we need careful synthetic methods, right? You're spending so much time in the Chem 312 lecture learning about all these different reaction types. And the reason that we need to have a good understanding of chemical reactivity is so that we can build more important molecules that can really change the world, right? Synthetic chemicals are used for drugs and materials every single day of your life. And so we want to understand how we can build up molecular complexity and understand the importance that that has in the world. So what is it that we're building this week? Well, this week we're actually building the imine functional group. So this is a reaction you should learn about in lecture. If you haven't learned about it yet, you will see it very soon. And it's the condensation or reaction of an aldehyde with an amine. So we can find our aldehyde on our starting material here. This is salicylaldehyde is this whole molecule. And the aldehyde itself reacts with an amine on our aminophenol to generate this final product. Now, the imine is this functional group here in the middle. This CN double bond is called an imine. It's kind of like a carbonyl, which is a CO double bond, but with a nitrogen in place of the oxygen. This particular molecule is actually called soap, not because it's a soap like the cleaner, it's because it stands for the acronym salicylic orthoaminophenol. And so that's what it's commonly referred to is a soap imine complex. And so we can generate this through this equilibrium process. Now, if we're thinking about equilibrium, you might have some flashbacks to Chem 128, where you learned about Le Chatelier's principle, where we talked about how chemical equilibrium is where the rate of our forward and reverse reactions are balanced. It doesn't mean that the reaction stops. It just means that as many products are being formed as many products are going back towards starting materials. So you might remember a picture that looks kind of like this. And this is Le Chatelier over on the right-hand side here, a good old picture of him. And the idea of Le Chatelier's principle is that when we are at equilibrium, if we change the system, our system will work to reestablish equilibrium. So equilibrium is this point where we have a steady rate or steady proportion of starting materials and products. And if we move away from equilibrium, our system will work to re-achieve equilibrium, right? So at this particular point, we are starting at equilibrium. And if we move away from this, our system will work to get back to this point, right? So if we stress the system, it will work to get back towards that point. So again, this is from Chem 128, so it might need a little bit of time to refresh this, right? So go back and read up a little bit on Le Chatelier's principle and equilibrium if you need to. We're not going to be doing any math with Q or K here, so that's good, but we will be doing math with stoichiometry and thinking about the yield of our chemical reaction. There's some help for that online as well, but these are also skills from Chem 127. So if we're thinking about our reaction for today, there's a few important considerations, right? So this is our imine synthesis at the top. And when we're running this reaction, we're going to heat it up. So we're going to be boiling our water or ethanol that this is going to be in, and the water is going to be leaving, right? When it's boiling, it's going to a gas and leaving. So the first question is I want you to think about how would equilibrium be affected if we're removing water from the system by boiling it, right? So that's our first kind of Le Chatelier throwback question that we can deal with. And the second thing to consider, second thing to think about is it turns out this imine product is actually highly insoluble in water. So these two bits of information are important when we think about how equilibrium is going to affect our synthesis. And so with that, let's go ahead and see how we make this imine. Here we have our scintillation vial that we are going to use to run today's experiment. So I've already weighed out our reagents. So our first reagent is going to be our aminophenol. And so here is our aminophenol, right? It's this brown solid. So I'm going to go ahead and add this into our scintillation vial. So we have our aminophenol in there. The next thing I'm going to add is our solvent, which is 10 milliliters of ethanol. So we can see here that the aminophenol is actually reasonably soluble in the ethanol. We have this nice brown solution that we might expect, right, if we had a brown solid that dissolved up. So we can give this just a quick little stir here just to kind of get things started. And the last thing I'm going to add is my salicylaldehyde. And I know that's a mouthful, but here we go. This is inside a syringe here. If you can see it, it's actually kind of a clear and colorless liquid. So our aminophenol was brown. Our salicylaldehyde is kind of clear and colorless. I'm going to go ahead and add this in here. So that was about 0.1 milliliters, sorry. And so we have this in our solution. So we're going to go ahead and heat this and let this reaction get started. So notice that the solution is still kind of brown. It got a little bit lighter, but that might be a little bit due to dilution. So we're going to heat this up and we're going to see what happens. So we can see that the color changed. Now it's much more of an orange color, and it's currently refluxing, right? That's the fancy word for boiling. And so what we're going to do is we're going to take this off the hot plate and let it cool back down, and we'll see what we get out from this chemical reaction. I gave it a little bit of extra time in an ice bath to fully crystallize, and so we're able to see lots of nice big orange powdery chunks in there. It kind of looks like orange glittery sand. So let's filter this and we'll see how much solid we were able to isolate. So here's our crystallized imine product. We were able to get 135 milligrams out. So you'll need this number in order to calculate the percent yield of this chemical reaction. So again, we started with our aminophenol as like a brownish powder, and our salicylaldehyde was a clear solution. And when they reacted together, we get this bright orange solid. So one of the big questions of this lab is understanding and explaining why the chemical structural changes, or the changes to the chemical structure, lead to a change in the color that we observe for the sample. Our imine product can actually be purified by recrystallization. So as things cool down in our flask, sometimes they can trap some impurities, including some of our starting materials. So I'm actually going to repurify some of this using a recrystallization. So I have 978 milligrams, or 0.978 grams of our imine product here that needs to get recrystallized. This is from an old batch of this synthesis. So this is not from today. That's why you can see there's little flecks of brown and stuff in it. So I want to get this nice and cleaned up for our use. So I have some ethanol that's being heated here on our hot plate. I'm going to add in this imine complex that we made today. Hopefully get as much of it as I can in there. Right, so that's 978 milligrams, or 0.978 grams. And we're going to let this all dissolve and then cool back down slowly, and we'll see how much we can purify by recrystallization. For my large-scale recrystallization, I was able to re-isolate 475 milligrams, or 0.475 grams of that imine product that we can now use. So this is from that larger scale recrystallization. Use this to determine the percent recovery for our imine product. So this relates to what we did last week in our previous experiment. So what's an application for this imine? Well, as it turns out, it can actually bind to metal complexes, and some of those are fluorescent. Fluorescence means that a complex is emitting light at a different wavelength than it's absorbing. So here we are under just white light, like normal room light. We can see that these two samples look nearly identical. However, let's turn the light down and shine ultraviolet light on these two samples. Right, when we shine this ultraviolet light on these samples, we can see that one is glowing green and one remains that yellow color. That green glow is because of a complexation with aluminum. So I added some aluminum to this left-hand vial, or left-hand test tube,
And that's what causes it to glow a little bit more of that greenish color. Whereas the imine itself doesn't really glow, right? It remains that same yellowish color. So this is the process of fluorescence. It's absorbing light in the ultraviolet region, and it's emitting this green light in the visible region.
The first part of this lab dealt with Le Chatelier's principle, equilibrium, and synthesis. But another thing we wanted to talk about in this experiment is actually why a compound might exhibit a color. So if we go back to our understanding again from general chemistry, right, we're building a lot on Chem 127 and 128 in this experiment. We learned a little bit about why a compound exhibits a color, and this is because it absorbs light in the visible region, right? If a compound absorbs light in the visible region, that's going to exhibit a color because we are seeing the absence of a particular set of photons when it hits our eyes. And we looked at this when we looked at absorbance spectroscopy, right? We have this plot of the absorbance, and we can see that some wavelengths are being absorbed and some are passing right through the system. Well, these wavelengths of light that are being absorbed have to do with the chemical structure. And one of the features that we can look at is specifically in Chem 312 that allows to identify whether a compound may absorb light in the visible region is the extent of what we call conjugation. So if we look at a chemical structure, such as our imine compound, what we notice is that this entire structure, right, is composed of atoms that are sp2 hybridized. So this ties back to hybridization that we learned about earlier in the term. And as long as we have this uninterrupted chain, this long chain of sp2 or sp hybridized atoms, we would predict that a compound would have a color. So in our imine complex, right, we have these two different aromatic rings, these benzene rings that you have seen as functional groups, and some of you talked about in your interesting molecule projects. And in the middle is a nitrogen and a carbon, right? All of these are sp2 hybridized. And these, what we would say is that this is a highly conjugated molecule because of all these sp2 atoms that are all lined up in a row. So if we were looking to determine if something may have a color or if something would not have a color, we would look for what we call an Sp3 road block, right? And the idea here is if we have something that breaks this conjugation, we might predict that it would no longer exhibit a color. So let's say we were to reduce our imine, and so now we have this sp3 hybridized carbon in the center of our chain. We would guess that this compound may not have a color, right? It may not exhibit a color like the imine does because we have one of these sp3 roadblocks, right? So there's a couple practice problems and a little bit more of a discussion in this in the PDF for you to kind of read through and see. In the experiment, what we actually saw was a process called fluorescence, which is a little bit different than just having a color. Fluorescence is harder to predict. That's not something we're really going into in this class, but the idea of fluorescence is a compound is emitting a wavelength that is different than the light that is being absorbed. And so in our case, right, we made this aluminum complex by mixing in aluminum with our imine. And so under normal light, this is what it looks like. It has this faint pale yellow color. But what we saw in the experiment is that when you shine ultraviolet light on this, right, it actually glows a brighter green color. And so we can see flashes of that green color under that UV light. And so it's absorbing ultraviolet light, which is outside of the visible range, and it's emitting green light in the visible range. And so that's the idea of fluorescence, right? That's the idea of even glow sticks and things like that. That has to do with a chemical process. But it's this idea that it's emitting wavelengths of light different than what are being absorbed. And so we can start to predict and think about the color of these compounds, and we can think about how we can build and synthesize more exciting, more value added compounds now that we are at the end of this lab.